Zeros of polynomial functions and their graphs. Greetings, I am Dr. Hart Simmons. Today I will be modeling an example of the two given objectives in the lesson. The first objective would be find zeros of polynomial functions. The second objective would be sketch graphs of polynomial functions. First, we want to recall the number a is a zero of the polynomial function if f of a equals to 0. Next, given the conditions, f is a polynomial and a is a real number, the below statements are equivalent. X minus a is a factor of the polynomial f of x. X equals to a is a zero of the function f. X equals to a is a solution of the polynomial equation f of x equals to 0. And for a comma 0 is an x-intercept of the graph of f. The example, find the zeros of the polynomial function f of x equals to 4x to the fifth minus 100x cubed plus 4x squared minus 100. Step 1, you want to set your f of x to equals to 0. So in other words, you can just remove the f of x and substitute in the 0. Now you want to factor the non-zero side. So you want to factor out your GCF if possible. In this case, by using the divisibility rules, we see on the left side that each term is has a factor of 4, so we can divide the 4 out. So the greatest common factor would be 4. So you have 4 times the quantity of x to the fifth minus 25x cubed plus x squared minus 25. All of this equal to 0. Part B is to substitute each term into the Punnett square of step 2. So the Punnett square comes from the biology area where you pretty much was talking about the recessive and dominant trait. But in this case, we will be using this to factor the polynomial. So as you notice that I removed the 4 by dividing both sides by 4 in order to place those terms into the Punnett square. So I have my leading term, which is x to the fifth, and my constant term, which is a negative 25. And you want to make sure that they are diagonal of each other. And the remaining terms can be diagonal the opposite way. Okay. And you setting this up so that you can find the GCF of each column and each row. So notice that when we look at the first column, we can take out x squared for our GCF. The second column, we can take out negative 25 for our GCF. For the top row, we can take out x cubed. In the bottom row, we can take out 1. That implies that we can rewrite this function or this polynomial equation as 4 times the quantity of x cubed plus 1 times the quantity of x squared minus 25 equals to 0. But we want to recall that for x squared minus 25, which is a difference of squares, we see that we have x squared minus b squared equals to a plus b times a minus b. So that implies that we can rewrite this as x minus 5 times the quantity x plus 5. Now for this cubic, we see x cubed plus 1. We have the property a cubed plus b cubed equals the quantity of a plus b times the quantity of a squared minus ab plus b squared. That implies that we can go back and rewrite this x cubed plus 1 as x plus 1 times the quantity x squared minus x plus 1. But notice that this x squared minus x plus 1 is a quadratic prime factor. So later on, you will see that I will have to use the quadratic formula. However, given the conditions that was in the previous properties, because x plus 1, x minus 5, and x plus 5 are factors, then we automatically see that x equals to -1, x equals to 5, and x equals to -5 are zeros of the function f. Now, to look at the prime quadratic factor, we see that we can use the quadratic formula, and you're utilizing like we did in the previous chapter. And in the end result, we see that x squared minus x plus 1 equal to 1 plus or minus I times the square root of 3, all divided by 2. So in other words, we know that this split into two zeros, and they are complex zeros. Thus, we have that the polynomial function have zeros. The zeros are x equals to -1, x equals to 5, x equals to -5, x equal to 1 minus I, the square root of 3, all divided by 2, and x equals to 1 plus I times the square root of 3, all divided by 2 for this function f. So the next component, we want to sketch the graph of the polynomial function. So we're using the same polynomial function. So the first step we would do is we would find the x-intercept, which is our a comma 0, and y-intercept, which would be our 0 comma b. We still have those equivalent properties or equivalent statements that was given in the previous slide. So we can see that -1 comma 0, 5 comma 0, and -5 comma 0 are the x-intercept of the graph f. Now we want to find the y-intercept, which is 0 comma b. So all we need to do is substitute 0 in for x and then simplify. And we see that the y-intercept would be 0 comma -100. Now for step 2, we want to plot the function's intercepts. Okay, so we see that we need -5, -1, and 5 for the x-axis, and we need -100 for the y-axis. So we have plotted the x-intercepts. Now we want to plot the y-intercept, which is a -100. So notice that the 0 divide the x-axis into 4 intervals. So we see that to the left of -5, we have the interval -infinity to -5. To the between -5 and -1 would be an interval. Between -1 and 5 would be an interval. And between 5 and infinity would be an interval. And we want to determine if these intervals are all positive, or all negative, because the sign do not interchange between those consecutive integers, within the interval. Thus, we will use this chart to determine if the interval will be all positive or will be all negative. So as you notice, I chose the x value -6 out of the interval -infinity to -5. When I plug it into the factors, x plus 1, x plus 5, x minus 5, and x squared minus x plus 1, we see that by plugging that -6 in, we end up with negative, 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 positive, respectively. That implies that when we multiply those together to get the product, we get a negative answer. that implies that that interval, which is negative infinity to negative 5, would be all negative. So now for negative 5 comma negative 1, we would choose the x value negative 4. So we would plug negative 4 into x plus 1, and we see we get a negative number. Same for x plus 5, we get a positive number. For x minus 5, we get a negative number. And for the last factor, x squared minus x plus 1, we get a positive number. And when we multiply an even number of negatives together, automatically we get a positive, and the positive times a positive will be a positive. So that product would be a positive. That implies that that interval will be a positive interval, the entire interval. The next interval would be negative 1 comma 5, and we chose the x value 0. So when we chose the x value 0, we can just plug it into each one of those factors, and we see that the product would give us a negative. And for 5 comma infinity, we chose the x value 6. So with the x value 6, we see that each factor, when we plug 6 inside, we get a positive. And when we multiply that product together, we get a positive. But also, you probably say, well, what about the 4? But 4 is positive as well. So you still will get the 4 at the end. So we want to apply these signs here to the graph. So notice that I put a negative to the left of negative 5. I put a positive in between negative 5 and negative 1, a negative in between negative 1 and 5, and a positive between a positive 5 and infinity, so that I can have an idea of how my graph should look. So before we even sketch this graph of the polynomial function, we want to choose the end behavior. So in a previous chapter, we talked about how to choose these different end behavior. You need to know what the degree is, and you need to know the sign of the leading coefficient. So in this case here, we see that our degree is 5 because it has the highest exponent. So that means that it is odd. So we will not be looking at the even component. We will be looking at the odd component. Now we need to look at the sign of the leading coefficient. Since 4 is the coefficient of this leading term, that let me know that we see that 4 is positive. That implies that we will be looking at these signs here. So as you notice that on the left side, it will be going down towards the negative, and on the right side, it will be increasing. Okay, so that means that we will have these endpoints here, which you see on the graph. On the coordinate plane, which I have placed there because we have not graphed yet. So now it's time to graph this polynomial. And we see that here we have this graph, okay? And notice that we have the endpoints that we were looking for. Notice that the intervals would be between negative infinity and negative 5. They're all negative y values. Between negative 5 and negative 1, we see all positive y values going up. Okay, so it satisfies all those different conditions and properties that we have gone over. And this is how it will look if you put it in the computer. So if you have any questions, please email me, and thank you.